Hey YouTube, we're back. Day 3 of our quarantine distance learning. Hope you're still doing well. Please remember that you can always reach out to any of us. We're dedicated to helping you and making sure that this whole situation doesn't affect you terribly. We will continue with our lessons from Mr. Boothman, who will come on camera in just a second. Please make sure you're doing your work. Please, we're putting in so much time and effort into this. It would be a shame if you didn't take advantage of everything that we're doing. All right, so let's get Mr. Boothman here. Let's begin. Happy Friday. Here we are again. It is College Friday. Okay, I'm sporting my purple Northwestern shirt. Feel free to ask me any college questions you might have during our Google Meet later today. I know you probably have some specific ones about our current situation, but I don't have many answers for you regarding that, but feel free to ask me anything that you need to, okay? Again, that will be during our Google Meet later today, along with your normal daily questions. Brief announcements, okay? Your exit ticket today is going to be the same as it's been the last 2 days. Just submit a question from today's lesson. I'm getting some fantastic questions. Please keep them up. In addition, you also have an AP Classroom assignment that I assigned a couple of weeks ago. As I've said before, I still expect that to be done. That needs to be submitted by midnight tonight. If it is not, then I will be putting in a 0 for now, since you've known about this for so long. And then I'll reach out to you and we'll work on getting that done later on. Okay. All right, today we're going to bounce back and forth between some new notes and your mastery sheet. So let's actually start in your mastery sheet. Okay, so you should be open to the second page now. So the first question on the second page, and it is an example problem. The region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of this solid. So we're building on what we did on the first page, but we're not dealing with simple shapes anymore. Okay, I'm not saying here is a circle and this is the base of a solid. Now we're dealing with slightly more complicated things. Let's start by drawing this graph. Okay, so f of x equals 2 plus x cosine of x. I did graph this in Desmos, and we get this very lovely graph here. I am going to focus on the part between -2 and 2. Okay, that's the interval we're looking at on our graph anyway. Okay, and between -2 and 2, so our graph kind of does something like this. It goes up, and then it starts going down, and then it goes back up a little, and then back down, and then it continues doing some weird stuff off to the sides. Okay, so this is our graph from -2 to 2, so we're only looking at this part of the graph right here. And here's what's new about what we're doing here. Okay. We're looking at what are called solids of revolution. So we are taking, and I'm going to erase the rest of this graph just to avoid any confusion. We're taking this specific piece of our graph, and we're taking this shape, and it is going to revolve, in this case, about the x-axis. So imagine, well, I had prepared this, but it's a little too small. We are taking this shape right here, and imagine that it is literally revolving. It is rotating about the x-axis. So here's the x-axis, and this shape is coming up out of the board, and it's sweeping through all of this space in between, and then goes back down into the board. And then if I could, I would demonstrate how this is rotating on the other side of the board until it comes back up and meets where it started. By doing this and rotating this shape through that entire space, we're filling in all of that space. We end up with a three-dimensional object with a volume, and we're asked to find that specific volume. Okay. So again, this is rotating up through the board, back into the board, and then back up and around. Okay. So we have the point where it goes back into the board, and then it continues rotating. Luckily, finding volume is going to work the same as before. Okay. So our volume is still going to be the integral of the area of a cross-section from one limit to another. So it's nothing new. It's not a new formula or concept. It's just much more difficult to conceptualize what this rotating is. Okay. And calculating or finding a formula for the area of a cross-section could be more difficult. Now let's start with what we know. Always a good place to start. We have our limits of integration from -2 to 2. And what is the shape of a cross-section? So if I slice into this, again, imagine it's three-dimensional. If I slice into this shape and pull that out, it rotated around the x-axis. So at any given point, it's a circle. Okay. And this shape goes all the way down to the x-axis, and then it's rotating around the x-axis. So the entire circle is filled in. So each cross-section of this pretty bizarre shape is a circle. And what is the area of a circle? Pi r squared. Renee, sit down. And what is the radius of this circle? So the radius of this circle, this distance right here, is going to be from the x-axis out to that point. So for any given x value, what formula gives us that height, that y value? It's just the function. Okay. And if this is the radius, then we're plugging this into the radius here. And it's being squared. And if this is the area of a cross-section, then we're taking this and we're plugging it into our integral here. And there we are. Now this would be very, very difficult to calculate by hand. Okay, you would use a calculator or some tool online. I'm not going to go through that calculation here, but okay, that's how we would finish it. You likely don't have a TI-89 lying around, so that's okay. That's about it. So even when our shapes are more complicated, as long as our cross-section is simple, and in this case it is, anything that's got any shape, no matter what this curve looked like, if it's revolving around the x-axis, then a cross-section is going to be a circle. Then finding the area of that cross-section and hence the volume, I won't say it's easy, but it is fairly straightforward. Okay. That's about to change. Now I won't say this isn't as straightforward, but it does get conceptually even trickier. So let's look at the second question on that page in your mastery sheet, and then once we go through this question, I'm going to go back and here's what we'll put in our notes after this example. Okay, we're looking at the region in the first quadrant enclosed by the graphs of y equals cosine of x. So cosine starts at 1 and it goes down like this, and y equals sine of x. So y equals sine of x starts at 0 and goes up like this. So we're looking at this region right here, the region enclosed by these two graphs in the first quadrant. And this area is revolved about the x-axis to form a solid. Find the volume. Like before, I'm going to erase all this extra stuff. We are revolving this here's our area, and it is coming up out of the board, around the x-axis, back into the board right there, and then through the board on the other side of the board, back up and around, and here it stops. It's quite a shape. So imagine this shape in 3 dimensions. Very difficult, I know. Now, as I visualize it, okay, we're seeing like a slice of it. This is kind of like a bowl, okay? Like a dog bowl, kind of, where the inside is just a little more pointed than usual, but then the outside is rounded, okay, and it's all filled in here. It's an interesting shape. To find volume, it's the same as before. This is always going to be our formula for the volume of these shapes. Let's start by looking at our limits of integration. So we're clearly starting at 0. We're stopping at this point right here, which is the point where sine of x and cosine of x intersect. So we did this in 8.2 before break. How do we find where two functions intersect? How do we find a point of intersection? We set them equal to each other and solve for x. So we're looking for where sine of x equals cosine of x. Now this will happen in an infinite number of places since they're trig functions and they're cyclical, periodic. But the first place it happens right here is pi over 4. It's the first place where sine and cosine are equivalent. So 0 to pi over 4. And now we need the area of a cross section. So let's imagine just any point here. What does that cross section look like if I'm pulling this slice out and I'm laying it on the board? Well, it's revolving around the x-axis, so it is a big circle. But is the entire circle filled in? Okay. It's filled in for all of this, but this area in between is going to be empty. And this is, again, also just a circle. So we end up with a shape like this. Okay, this is known, I'm sure you're thinking it looks like a donut of sorts. Anyone who's handy with anything knows that this is also a washer. So we actually call this a washer. It's the technical calculus term for it. And this method of finding volume using this way is known as the washer method. Now, how do we find the area, the actual filled in area here of this cross section? Well, we have one big circle, okay? And the area of that big circle is going to be pi times whatever this big radius is. And I'm going to use capital R to describe that radius, squared. Now, what is that big radius, big R? It's that distance right there from the x-axis all the way up to our top function. Now, what is that top function? Was it cosine or sine? In this case, it was cosine. So for any given x value, the height there is just the cosine value for that x value. So the area of the entire circle is pi times cosine squared of x. And if we just want that filled in area, we need to subtract this smaller area on the inside. I'm going to call that little r, little radius. And the area of that is pi little r squared. And what is little r? That's the distance from the x-axis up to this first function, which was sine. And to find the filled in area then, we need pi big R squared subtracting that smaller circle on the inside. In this case, it's going to be pi cosine squared minus pi sine squared. And to make it a little simpler, we can actually factor out that pi. So this is the area of a cross section, the area of a washer here. we evaluate this integral? To evaluate this integral, we would actually need to use one of our wonderful one of our wonderful trig identities. It is not a Pythagorean identity. It is a double angle identity. And from here, we could calculate this by hand. I encourage you to work through that on your own. I'm going to jump straight to the answer, which is pi over 2. Okay. Would you be expected to know that identity? No. It would be nice if you could do things like that. I'm not going to say you absolutely don't ever need it. But in general, if you see a question that's this complicated, you would likely have access to a calculator on the AP exam. Okay. But there's our volume. And we don't really have units here. You could put units cubed, but that's fine. All right, this is known as the washer method. And right now we're just looking at the washer method for shapes that are revolving about the x-axis. Let's jump back into our notes because I do want to generalize this just a little based on what we just did. So in our notes, this is still section 8.3. And we have washer method. Our volume is going to be the integral from a to b of, we have each cross section is a washer, so we have a big circle, pi big R squared, and subtracting the smaller hollow part of the shape, that's pi little r squared, dx. We typically factor out this pi. You could leave it in, or you can pull that constant out of the integral. Either one is fine. And in general, this is our formula for washer method. Note that your work here would be to determine the limits of integration, as well as the radius of the large and smaller circle of the washer in terms of x, since we're revolving about the x-axis. That's all I wanted to do for today. I'm not really going to force you to start any other practice right now. If you would like, then the next page of your mastery sheet at the very top, those first 4 questions are great practice. We're going to work on that on Monday in class as well, but it would be a great idea to get started, at least work through one of them, so you start to get the hang of this. Use Desmos to graph if you need to, by all means, unless it's a simple enough function. Remember that you are expected to be able to graph those simpler functions by hand and recognize their shapes. We will continue talking about the washer method for the next week. Okay, we just revolved around the x-axis. Next week we'll look at what happens when we revolve about the y-axis and lines other than the x and the y-axes. Okay. So please come to the Google Meet today if you have any questions about this. By midnight tonight, please submit your exit ticket, a question about today's lesson, in addition to your AP Classroom assignment. All right, well, that's it for today. Please enjoy your weekend. Please let us know if you need absolutely anything. And make sure you hit that like and subscribe button.